All right, hello everyone, and welcome back to Physical Geology 1403. Today we are going over Lecture 5. We had to miss one day of class for this section, which is unfortunate, and does put us a little bit behind in the schedule because of the snow day, the half snow day we had on Tuesday. It does put us a little bit behind here. But we're going to try and make up for that by next week. Instead of having lecture 6 on Tuesday, lecture 7 on Thursday, and then the exam the next week, really the only way I can see a way around getting through being behind is we have lecture 7 and our exam review on Thursday, a week from today. And then you have the exam open over the weekend. So I'll make it up to you by giving you Thursday afternoon to Sunday evening to take the exam. So you'll get almost 4 days to take the exam instead of the 2 you would have gotten otherwise. Sound like a fair trade? We double up on content basically on Thursday, but I give you twice as much time to take the exam. Sound fair? Okay, fair trade. Okay. Before we jump into today's content, are there any questions or comments you guys have? Anything interesting, scientific you want to talk about? Anything else? It doesn't have to be related to geology.
Are you feeling better?
I am absolutely feeling better. Nose is still just a little stuffy, but honestly, I think that's mostly due to the dry air. My nose tends to struggle with the dry air at times. So I think that's probably what it is at this point. I'm not anywhere near feeling as bad as I did last week. Thank you for asking. As a matter of fact, I ran 2 miles this morning. I was just like, it feels good to be back at it. You know, you, yeah. I'm training now. I mean, I run a few times a week, but now I'm trying to really get back into it because I'm training for my first 5K, which is in 3 weeks. I've done it before. I just haven't done an official 5K. So, okay. Let's see. I'm trying to think if there's any really interesting, not too long to talk about things, like fun facts. This is the problem with being like a scientist. You know so many fun facts, your brain is just filled with all these relatively irrelevant facts. Like I could talk about a million things right now, but I don't know that y'all would necessarily find them terribly interesting. I don't know. What makes you guys interested in science? Like when somebody says something, you hear something on the radio, you see like an article in the news, be like, oh, well, that's really cool. I never knew that. Or I wish I could know more about that.
I just like knowing how things work.
You like knowing how things work?
But if they're not relevant to me, I won't care.
Really? So you care a lot more about like I don't know, the engineering of like a combustion engine, like how that works instead of like how a black hole works.
Kind of.
Okay.
I mean, that's not something I care about.
Oh, you don't care about engines either? Yeah, fair enough.
That's what I have a husband for.
Oh, I see. Yes. Gotcha.
No, I care about I was really into chemistry because I like to bake.
Food chemistry. Yeah.
But I mean, I'm also an extremely curious person, so I also like knowing how things are kind of completely unrelated, like black holes and stuff, like the possibility of those.
Oh my goodness. Black holes are a fascinating subject. Let me tell you. What? Am I good at math?
What kind of math?
Adequate. Why?
College algebra math.
College algebra math. That I can, but
I took that last semester.
probably not right now.
Bacon, I had her.
Oh, Cecilia.
Yes.
Yes.
Interesting class.
Interesting class. Okay.
Yeah.
I can't help you right now.
She makes you write down all the notes.
Good.
No, it's all. It's a lot of notes.
I'm sure it's a lot, but you know my philosophy on notes. The more notes you take, the better equipped you are. That's my philosophy. Except I don't make you write down everything. The quality of your notes is its own reward in my class.
For the homework, because she records you the lectures, if you are able to do a split screen on your computer, watch the lecture video while you do your homework.
Well, I did, but it's just this one question of finding the domain and range of the function.
All right, we're getting off track. Let's bring it back. I love that you guys want to collaborate, and I'm going to encourage that. But, okay, if there are no actual, questions, then we'll just jump right into the stuff. There are things that I can talk about, but I'll bring those up another time, maybe. Okay. Weathering. Last time we talked about, or in the previous weeks, we have talked about minerals, and then igneous rocks, and then volcanoes and how those work, those external volcanic processes. So now we're continuing through our rock cycle. So we've gone through magma to intrusive bodies and volcanic activity. Now we've seen the lava and magma has turned into igneous rock. What was next in our rock cycle? Things get exposed at the surface, and weather. What is weathering, though? If you had to guess, what would weathering be? Okay, used a word there, erosion. I'm going to come back to that in a minute, but you also said the wearing away of rocky material. Okay. Anyone else have any other definitions, or do you agree with that? I will pull the participation out of you. Yes? How you doing, Alani? You're alive? That's best you can hope for today? All right. Anything I can do to help? No? All right.
Give her 100 for the day and send her home.
I'll give you 100 for the day. Well, you're here, so you have 100 on attendance. Way to go. Okay.
I can add by the elements.
Oh, by the elements. What are we talking about? Fire, earth, fire, wind? Yeah, well, I mean, those are the fundamental elements as people typically refer to them. Or are you talking about the periodic table of elements?
Wind, water, all that stuff.
Wind, water,
Anything that can, break away the material.
earth, wind, and fire. Yeah, okay. Well, you are right in that weathering is the breakdown of a material. Now, you said a rocky material. It doesn't have to be a rocky material. Any material can and often does weather. Okay? Even we weather. Weather is the breaking down of a material. Okay? Now, why does this happen? Weathering happens as a response to a new environmental parameter. What does that mean? Well, if I change the temperature in this room, some of you in here are wearing jackets. For some reason, Emma's wearing a parka, like an Eskimo or something. But if I turned the temperature up or down, we would either put on or take off sweaters accordingly, right? We are adapting, we are changing, responding to a change in our environment. That's a choice you and I make, but everything else in nature does that as a rule of physics, okay, or chemistry, or by instinct in the case of animals, okay? So if I have a material that is formed in another environment, a different environment than we have up here, and then expose it to the conditions here, what's it going to do? It's going to change in response to that environment. Classic example I've already given you, olivine. Olivine is a mineral that we see often form in the mantle. What are the conditions like in the mantle? Hot and there's lots of heat
Pressure.
and lots of pressure. Bingo. Okay, so there's lots of heat, lots of pressure. Then we get that intrusive body gets shoved up here through tectonics. What do we not have up here? Rude. My mama's still up here. Hey, would you grab the door for me on your way in? Thank you very much, Adriel. Okay. The mantle is very hot and has a lot of pressure. And what are we lacking up here?
That amount of heat and the pressure.
Heat and pressure, right? Extremely low in both categories compared to the mantle. And so that olivine, which was formed at high heat and high pressure, is going to come up here and break down in response to new environmental parameters. That is to say, a lack of that heat and pressure. It's going to break down until it finds a new stable condition, because in general, all things in nature are seeking that state of stability. Okay? Olivine is no longer stable up here, so it breaks down into something else. We'll talk about what it breaks down to later on. Other things do this besides minerals, though. What is a plant? A plant dies. What happens to it after that? Decomposes. Same thing happens to us, by the way. Matter of fact, it happens to us even before we start dying. You know why you get old? It's not so much that you're decomposing. What's actually happening is your DNA is getting exposed to oxygen. Oxygen is oxidizing as a reactive process bits and pieces of your DNA. So as your DNA, which has certain missions, certain codes, right, to cellular, to regenerate your body, its cells as they die, your skin cells, liver cells, all of that, as your DNA is working over time to replace those cells, it's also oxidizing, which reduces its efficiency. Okay, so as time goes on, your body's DNA cannot keep up with the demand of upkeeping your body. We call that aging. This is a response to the oxidization of your DNA.
So oxygen is killing us.
Oxygen is killing you, but by the same token, we need it to survive. We respire it. We need to breathe it. So oxygen is simultaneously keeping you alive and killing you. Isn't that interesting? So this is an example of what biological things do as time goes on. Okay, you can think of that as a form of weathering if you like, but when a plant dies and it no longer can upkeep its cellular regeneration, it completely breaks apart. That is weathering. What about rust? What happens? What is rust? Stuff you pour Coca-Cola on. Interesting. It is the oxidization of metals. What's happening there? You get oxygen dissolved in usually water, and that water, when it comes in contact with the metal, the free oxygen that's dissolved in that water attaches itself to, say, the iron, and all of a sudden you have iron oxide instead of iron. Okay? Instead of just iron, I should say. Okay? And that flakes off. It falls apart. It takes on that reddish appearance, that reddish-brown appearance. Okay, this is rust. This is a response to an environmental change. That is the addition of oxygen to my metal. Okay? So, this is one aspect that's constantly happening of how Earth is dynamic, constantly changing. Remember? That's what dynamic means. So this is a process that occurs on the surface, which means that it gets its energy from the sun. Okay, this is one of those processes powered by the sun that we learned about last time. All right. Now there are three terms that I need you to get familiar with here. The first one is weathering. Weathering being the breakdown of that material, like you can see right here. Now this is obviously a form of artificial change, right? We're impacting this with a chisel, breaking it apart, but you see my point. This is breaking down the material, okay? Then there is erosion. Now, this is a word that Lexi used earlier, okay? Erosion is actually different from weathering. They are not the same thing, even though in our society and in a lot of science classes, they use them in the same way. Erosion is actually only the transport of that material. Weathering is the breakdown. Erosion is only the transport of the weathered material. So if someone looks at a mountain and says, "My, look how much that mountain has eroded away," that's actually incorrect. It has weathered away. It has broken down through the process of weathering. The pieces have been transported away through the process of erosion. Okay?
So what if somebody says that something's eroded through something?
That is also incorrect. So erosion is just the transport mechanism. if we're trying to describe how something has changed physically, how something has lost components of itself, it's weathering. Okay? So that's incorrect terminology. All right? So, and then there's a third part here called mass wasting, which I'm only going to mention right now, but is going to be much more relevant later on in the course. We're going to spend more time on it in Module 2, called mass wasting. Mass wasting is what we call it when gravity is the driving force behind the motion. So you could think of it as a subset of erosion, if you like, but it is not being pushed or pulled by wind or water. This is purely happening under the influence of gravity, and so it kind of has its own category here. And we will talk about that more at a later time. All right, there are two types of weathering that you need to know about. The first type is mechanical weathering. This is the physical breakdown of your material. Okay, so if I were to hit a rock with a hammer, technically that would be a form of mechanical weathering. Artificially mechanical because I'm doing it. But I mean, rocks fall all the time. They tumble down a cliff and they crack open, or something hits them, something heavier hits them and they crack apart, right? It's an example of mechanical weathering. I'll give you some other examples of mechanical weathering here in a minute. For now, let's talk about mechanical weathering rate. The smaller my particles become of my total mass, the faster weathering will occur. What do I mean by that? If I have 1 cube of granite here, a 2 by 2 cube of granite, and then break that into smaller pieces, and then those into even smaller pieces, my rate of weathering, the rate at which this continues to break down, is going to increase. It's going to weather faster if I have smaller pieces. Why do you suppose that is? Well, if there's less of it to weather away, wouldn't it weather slower? It's okay if you read the answer off the slide if you recognize that it's the answer. Yeah, why does surface area have anything to do with it? Well, weathering is something that happens to a material when that material comes in contact with a new environmental parameter. Where does contact occur? On the outer surface. The outer surface of my one block here only has 24 square units if it's 2 by 2 square. The more small pieces I break it into, the more surface area is exposed to that environment. So we break it into smaller pieces, 48 square units. Even smaller pieces, 96 square units, so on and so forth. So more surface area means more exposure, which means more opportunity for weathering to occur. A simple example of this would be if you took a teaspoon of sugar and a sugar cube, and you dropped each of them into a cup of tea, or whatever your preferred beverage of choice is, and you mix it up, which one dissolves faster? Yeah, the grains, the individual grains of sugar, the sugar cube takes longer to dissolve, less surface area. Okay? Now what this means is, if surface area is the big factor here, objects that have corners are going to weather those corners faster than the sides. Okay? So if I have this cube right here, and I drape a piece of cloth over this one side, and then cut it apart into that exact dimension of this one side, and then I take that fabric and I drape it over this corner, I'm all of a sudden going to have more surface area under that fabric than I would on the side, because I'm taking some of this and some of that and some of that side. Okay? And so because corners have more surface area, they're going to weather faster than this. Okay? And that is why you get rounded rocks in places that have running water. The beach or a river or a lake will have rounded rocks because corners weather faster than the sides do. So some examples of how mechanical weathering can occur. Frost wedging. Frost wedging is what happens when water works its way into cracks in a rock, like in a cliffside, and then we get cold temperatures that cause it to freeze. What happens to water when it freezes? It expands. Yes, it does. We're going to talk about this when we learn about glaciology. Okay, it expands by about 9% its volume. Okay, so as it's expanding, what's it going to do to that crack in the rock? Yeah, it's going to make it crack it wider, right? Thank you. Okay, so as it cracks it wider, the water can work its way in deeper. As it works its way in deeper, it's going to freeze again and then push that crack wider again, and so on and so forth, year after year after year after year after year, until finally pieces of rock fall off the cliff as a result of this. Frost wedging, we call it. Salt crystals do something similar. When you have water that contains dissolved salt and it gets washed up onto rock layers, it'll work its way into the cracks in that rock. The salt will form crystals as the water evaporates away, and the larger the crystals grow, the more they push pieces of rock out from that edge, from that open face, and you actually end up with these pockets in the rock like that. Okay, we call that salt crystal growth. This is actually also a big part of the reason why our roads are in such bad condition after winter is done. Because what do we put on our roads whenever it gets icy? Salt. What's that salt going to do? Cole, what do you think? When you put that salt on the ground and then your ice dissolves away and then the sun comes out and it evaporates all that melted ice water, what happens to the salt? Does it evaporate away with the water? No, it stays behind. And where is it going to stay behind? Yeah, the cracks in the road. And what happens as it gets into the cracks in the road, the more water evaporates away, the larger my salt crystals become, and they push those cracks wider. And that's why we get potholes all over the place in the winter. Okay? I actually, on my way in, I don't know which way you guys come from. I came in from the gym this morning. Our speed bump over here next to the Globe Theater is broken apart. There was a big old crack in it before, and now it's completely shattered into two pieces. I'd say that probably has something to do with two factors: the freeze and the contraction and expansion of the asphalt to the cold temperatures, and also the amount of salt that we put down that worked its way into those cracks. Okay, anyway, it's broke. And there are a bunch of potholes in the road on 87th on the way to my house.
I think they're trying to change that because by my house they put dirt down instead of ice.
There you go. Okay, so in places up north, the northern states where I used to live, they haven't put salt down for a long time. They use volcanic cinders like ash or sand, which does not melt the ice, but it does give you extra traction for driving on it. Then it's much friendlier for your roads. It's much better investment. You don't have to spend millions of dollars repairing your roads every year. So if you're saying that they do that around here, then that's great. It's a better investment.
I think that's what they were doing on JBS, because when I was coming from work one day, it was all muddy.
Very possible. Also, there's already, plenty of dirt lying around in Odessa, so.
It seemed excessively muddy. In my
Could have been.
mom's hometown,
Yeah.
there's a sign right when you pass like the hospital. She's from a real tiny town,
Mm-hmm.
and it says "Welcome to Pothole City."
Pothole City. Yeah. You guys know how much money it takes to make one mile of road?
Probably a really dumb amount.
$1 million to make 1 mile of road. Do you know what the Ector County road budget is for the year?
$500,000.
$2 million.
So we get 2 miles of it. Fantastic.
Yeah, you can build or repair approximately 2 miles of road a year for the budget that Ector County has. And yet people complain all the time with how much taxes they have to pay. All right. You know how much Midland County gets? $56 million.
Of course.
They pay more taxes. They get nicer roads. Okay.
I can't even imagine with how steep some of the exits are and everything, how bad it was driving on them.
Oh, I imagine. Yeah, there were places here in town that were not fun to drive through either. Go down University Boulevard. Once you get past Dixie, all of a sudden it's Ice City. I used to live there.
Headed,
Towards college. Towards here.
oh,
Yep.
yeah, that's kind of coming.
Yep. It's not fun. Okay, so some other examples of mechanical weathering. When you have one of those intrusive bodies, like a batholith or a stalk or a laccolith that we learned last time, when they get exposed at the surface, they are under very different conditions than they were underground, like that olivine we talked about earlier. Underground, they formed in lots of heat and lots of pressure. Okay? Lots of heat and lots of pressure made a very dense, compact rock. Well, now it's here at the surface, under much less heat and much less pressure. How's it going to respond? It's going to expand. But it does so from the outside in. And so what happens is you get almost like layers of rock, like shell layers of rock that separate from the inside part, and they crack off and fall down. We call this sheeting. Also, this is called exfoliation. That's another term for it. But it looks like layer after layer after layer of eggshells are falling off of this rock. Okay, off of this intrusive body. Then biological activity can also create mechanical weathering. Have you ever seen a tree growing in cracks in a rock? Yeah? Good. So as that tree or that plant is growing, what are its roots going to do? Yeah, they're also going to grow. Right. They're going to grow, they're going to push deeper, they're going to get wider and fatter, and they're going to push the rocks on the outer edge off. Like this guy. Eventually, that rock is going to fall down. Okay? Any questions about mechanical weathering? The second type of weathering you need to know is called chemical weathering. Chemical weathering is basically the dissolving of a material into another material, like with that sugar that we talked about earlier, or salt. Okay? Now, when you dissolve something, it doesn't just disappear. Its components are still there in the liquid. If I dissolve water, or if I dissolve sugar into water, I'm going to make sugar water. That sugar is still there. It's not all of a sudden gone. So if I start evaporating that water, eventually I'm going to reach a point where I do not have enough water left to keep that sugar in a dissolved state. And that sugar will reprecipitate into crystals. Okay? So I can dissolve a substance and I can essentially undissolve it by removing the material that I dissolved it with. Okay? Just bear that in mind. So water is a very common method for chemical weathering to occur. Something needs to be dissolved in that water, though. When there's oxygen dissolved in that water, we already talked about what that does. It rusts metal. Okay? A lot of metals respond to oxygenated water. Iron will rust red. Copper will, it's more or less rust. It's not exactly the same, but it's more of a tarnish, but it will tarnish green. The Statue of Liberty. What color is the Statue of Liberty?
Green.
Green. What metal is it made out of? What color is copper?
Brownish, tan.
I don't have my copper out here anymore, but I've got a big old chunk of it out in the display cases. Yeah, copper is a beautiful, shiny, kind of brownish color.
Like burnt orange.
Almost burnt orange color. So then why is the Statue of Liberty green? It's tarnished over the years. Imagine, for the first 10 or 12 years after the Statue of Liberty was built there by the French, yes, the French built our Statue of Liberty, it was brown. It wasn't green. We only think of it as green now, right? Imagine how weird it would have been for our great-great-grandparents watching that brown Statue of Liberty slowly turn green. And now we just take it for granted, okay? Okay, well, that's what happens when oxygen gets dissolved in water. What about carbon dioxide? When carbon dioxide gets dissolved in water, you make something called carbonic acid. Okay, now that doesn't sound very good, and to be fair, it's not great. Carbonic acid will dissolve a lot of stuff given enough time. Have you ever heard the term acid rain? When I say acid rain, what do you think of?
Everything melting.
Right, everything melting. That's not actually how acid rain works. To be able to melt everything requires what is called a molecular acid. Those do not occur in nature. Those are artificial. We have to make those in a lab. Carbonic acid is 99% of the acid rain that you're going to hear about in the world. Because carbon dioxide is very common, and the concentration of carbon dioxide in the atmosphere is only increasing, right? So the more carbon dioxide there is in the atmosphere, the more carbonic acid falls in our rain. Well, carbonic acid isn't going to hurt you and me and most of the materials that we look at least not in the short term. It will dissolve minerals. It will, in high concentrations, be hostile to other things like paint, like wood, like plants. If there's a high enough concentration, it'll be harmful to plants that try and absorb it. Okay, so that's what we're talking about. It's not strictly dangerous to us. Now, you can get, in proximity to a volcanic eruption, you can get sulfuric acid rain, which is not good. That's definitely more harmful, and you definitely don't want that to happen. But again, that's only near volcanic eruptions that are actively spitting sulfur dioxide into the atmosphere. Okay? But this carbonic acid is slowly going to dissolve minerals. As a matter of fact, it will dissolve a lot of the minerals that you learned about in Lab 1. Calcite, as an example. Calcite, CaCO3, when combined with carbonic acid, will be broken down into loose calcium ions and bicarbonate ions, both of which are used by certain organisms in the ocean to make their shells. This is how cave networks form. For those of you that don't know or haven't explored my YouTube channel at all, I am a caver. I'm a cave guide for the Texas Cave Management Association. I go a couple times a year. I actually have a trip that I need to plan for later this year. But we go and explore a bunch of the caves here in Texas. So what happens is carbonic acid washes its way underground and slowly dissolves limestone layers. Limestone is a type of sedimentary rock you're going to learn about on next week, made entirely out of calcite. That calcite will dissolve in the presence of carbonic acid, leaving empty spaces underground, which we call caves. Okay, so that is a chemical weathering result. Now, calcite isn't the only mineral that dissolves under the presence of carbonic acid. Again, a lot of them will. For example, potassium feldspar, a principal component in granite, okay, will break down. Feldspar, in the presence of carbonic acid with the water that acid came in, will break down into clay, which is a principal ingredient in soil, potassium ions, bicarbonate ions, and silica ions. Potassium, most living things require potassium, so it's going to get utilized by some plant or animal somewhere along the water chain. Okay? Bicarbonate. What is bicarbonate? Who here likes Odessa water? Right, no one does. It is rich in a whole bunch of different mineral ingredients, dissolved mineral ingredients. A very common one is bicarbonate. You know that really annoying white crust that builds up on all of your appliances that use water, like your dishwasher and your water heater and your garden hose and stuff like that? Or have you ever left a glass of water out until it evaporates away and there's kind of this white dust left inside your glass? That's bicarbonate. Okay, that's the result of chemically weathered silicates, basically. That includes, well, not all silicates, but that includes calcite, and it includes feldspar. Okay, so this bicarbonate, that's in our water, and then silica. Silica, in its microscopic form like this, will get washed through our groundwater system until it finds an empty space. That empty space, it slowly starts to build little micro layers inside of. And as more of it gets washed through, pushed through these empty spaces, it fills those spaces in layer by layer by layer by layer until they are completely filled in. And that is where you get agates. Agates like this, and geodes are formed through this process. Okay? All right, So now we're going to work our way through a little bit of a logic train here. Okay, I want you to work together to come to a conclusion about a question I'm going to ask. How many of you have ever been to Hawaii? No? I think I asked this before and none of you have. Okay. Hawaii has red soil, red dirt. Can you explain to me why Hawaii might have red dirt? Think about that for a second. I'm going to give you some more information and then I'll come back to that. Okay? When you chemically weather quartz, it breaks down into silica. And we just talked about what happens to that. You make your agates out of it. Feldspars, which are very common, break down into clay, which is the basis of a lot of soil, plus loose silicas, potassiums, sodiums, and calciums. Amphibole. Okay, now we're talking about dark silicates. It's going to break down into clays, sure. Also, limonite and hematite, which are iron oxides. Olivine, another dark silicate, breaks down into iron oxides. So now with that extra information, let me ask you again, now that you've had a little bit of time, why would Hawaii have red soil? Sure, I mean, yes, it is rich in minerals, but everywhere is rich in minerals. What minerals are you talking about? Which ones?
Feldspar, amphibole, and I feel like those might be the only two since they are the clay minerals. So isn't red soil just rich in clay?
No. No. What do you suppose is making the soil red? And I want to hear from anyone and everyone here. Okay? Adriel, what do you think? What makes things red? We already talked about a few red things today. What made those things red? Oxidized what? Yes, oxidized iron. Iron oxide is red. Remember we talked about this? Rust, right? Rust is red, right? Good. Okay, so oxidized iron is red. Why would it be in Hawaii's soil, though?
Our brains are still defrosting.
Still defrosting? It's okay. I am a patient teacher. I have no trouble waiting. How about I give you...
Doesn't silica have iron in it?
Silica does not have iron in it. What does have iron in it?
I forgot.
Jared, what do you think? Let me get out of your way. What minerals have we learned about in our class that are rich in iron? For a mineral to have iron in it, puts it in what category of mineral? Please pull out your notes. This is an exercise we are doing. This is a thought exercise. I'm trying to help you tie together multiple ideas that you've learned over the last few weeks. Okay? This is science. I don't just talk at you, I expect engagement. Which classification? Huh?
The olivine.
Okay, so sure, olivine has iron in it, but my general question was, what classification of mineral has iron in them? Olivine is an example of what type of mineral? Dark silicates. Thank you. Okay, so we have two types of mineral, right? Light silicates and dark silicates. Dark silicates are the ones that are rich in iron and magnesium. What composition of rock must Hawaii be made out of to have rich quantities of dark silicate minerals? Igneous is a type of rock. What composition, what igneous composition would have lots of dark silicates in it? So pyroclastic is a texture that you get from volcanic eruptions. What I'm looking for is a type of composition. What igneous composition is rich in dark silicates? Mafic. There it is. Mafic. Remember, Ma, think magnesium. Fic, that's the suffix for iron a lot of the time. Okay? No. Thank you very much for consulting your notes. That lets me know that you have taken notes, and taking notes is vital in my class, okay? So, mafic composition, okay? So if Hawaii is mafic, why is Hawaii mafic? Well, what is it sitting on top of? It's made by volcanoes, but what is Hawaii sitting on top of? An oceanic plate or a continental plate? Oceanic plate. And what's the composition of oceanic plates? It's mafic. Perfect.
That seems like it would not be the other one.
Okay. So we have identified all the steps here. Now let's tie it together with these ideas. We have an ocean plate. Mafic in composition, thin, dense, through which comes mafic magma from the mantle. Mafic magma goes through mafic plate, does not change compositionally there. There isn't much time for Bowen's reaction series to occur. So we get mafic lava expelled at the surface, which builds layer upon layer upon layer upon layer upon until you get this island that comes out of the bottom of the ocean, peeks its head up above the ocean. Boom, you get Hawaii. Mafic island, Hawaii, full of minerals, dark silicate minerals, rich in iron and magnesium. What happens to those minerals? They weather. As they weather down, what do we make? When dark silicates weather, what do we get? Clay and limonite and hematite, which are iron oxides. And what color are iron oxides? Red. So using ideas that you got in the last 3 lectures, we have answered this simple question: why does Hawaii have red soil? That might not even be a question you get in a geology class. Someone could just ask you that one day. You're just out on vacation and be like, why is the dirt red? Now you can tell them. Boom, okay? Not only, that situation may never come up, but this is an important exercise for taking multiple ideas and tying them together to make a conclusion, okay? It's a vital skill in critical thinking.
I hope nobody's on vacation in Hawaii and the one thing they're wondering is why is the dirt red?
Clearly you've never been on vacation with me, right? Okay. But this is an important exercise for, the rest of my class too, because this is not the last time I'm going to do this, right? Tying ideas together is an essential aspect of science. So get ready for another one at any point in time, all right? Okay, Something else that can happen here is as our water bearing some dissolved substance kind of makes its way, percolates its way, gets soaked into the rock, it will have some sort of effect. And sometimes those effects can make these kind of weird looking, almost bubbly blisters. We call that spheroidal weathering, okay, where it kind of bubbles up and then breaks off in these sort of shelly layers, bit by bit by bit by bit. Okay, so that's another thing we can see from chemical weathering. Now, as weathering continues, certain things are going to weather faster than others. Now, this has a lot to do with whatever the composition is that we're talking about, the composition of our material. But it also has to do with the environment. How much water is falling? If there's not much water falling, am I going to get the influence of much acid? No, I'm probably not. Right? So there's a lot of factors that go into this. But when one material weathers faster than another, we call that differential weathering. Here I have two gravestones. Which of them is older? One or two? One? Right, it's pretty clearly one, right? It's actually two. I know. I said no trick questions in my class.
1868, it looks like. But they also, like, you can tell they're weathering different because that one's still smooth and that one's bumpy.
Exactly. This one looks like it should be older, but it's not. What then is making it look like that? They built it out of a material that weathers faster than the people that built this one did. This one's actually made out of marble, which is what happens when you metamorphose limestone. Limestone's made out of calcite. Calcite dissolves quickly in the presence of carbonic acid. This one's made out of granite, weathers slowly in the presence of carbonic acid. So even though this one is older, the material of this one weathers faster. Okay? That's differential weathering. And look at that. You now know how to get good countertops and make good gravestone choices. Man, my class is so practical. Okay.
Yes, we're definitely not going to forget all this in the next 70 years.
Hey, you'll need to buy countertops and gravestones sooner than you think, maybe. I don't know. Adulthood comes quickly, whether you want it to or not. Okay. Any questions about weathering before we move on to our discussion on soils? Okay. When I say soil, what do you think of? Dirt. The stuff you kick it around. I'm just imagining Lexi now going in people's yards and just like kicking clods of dirt everywhere.
No, when I was in T-ball when I was 3, I would play with the dirt in the infield, and my coach literally picked me up and said, play with the dirt out here.
Play with the dirt over here. That's funny. All right, what else? Sergio. You alive, brother? No worries. When I say soil, what do you think of?
Soil?
Yeah.
Ground? Like plants?
Right. Yeah, plants, ground, good. Okay, these are all good. Soil is actually, do you want to keep up? If I push it again, it's going to freeze. Oh, okay. No, it only skipped. Okay, good. All right, so soil is actually very, very, very important to you and me. Our entire biosphere relies on the presence of soil. Why? Sergio just said it. What happens in soil? What do we do with soil? Grow plants. Yes, plants grow in soil. Plants require soil. Without soil, no plants. No plants, no animals, and no oxygen. Yes, our entire survival on this planet is dependent on the continuation of soil. Okay? So that's why it's very important for us to study, understand, and protect. Okay? So what is soil? Soil is a collection of four things: air, water, humus, not hummus, humus, okay? Humus is decayed organic matter, and mineral matter, okay? Those are the four things that make our soil. In different quantities, different ratios with each other, you'll get different types of soil. Generally speaking, you want a lot of mineral content, less organic content, and the ratio of air and water it fluctuates a lot back and forth between the different types of soils. For example, here in Odessa, do you think that we have more air or more water in our soil? Probably safe to say air. Do you think we have more organic content or mineral content? Mineral content, pretty safe bet. What about in the Amazon? More air or water? More water. What about organic content or mineral content? Organic content, okay? So here we have just two simple examples of how widely diverse the soil can get across our planet, okay? So let's talk about the factors that influence that soil. First is the parent material. Parent material is what the mineral matter is made out of. Now, the mineral content in my soil is going to come from the mechanical and chemical weathering of rock. If my soil has mineral content from rock that broke down, that was weathered locally in that area, we call that a residual soil. So if the soil here in this valley is made by the rock that weathered down from this cliffside or that cliffside, okay, we call that a residual soil. But if this river washed sediment downstream from who knows how far, and then that sediment got incorporated into the soil here, we call that a transported soil, okay? We can tell which one it is by looking at them chemically, okay? That's true to an extent. As more time goes on and as more plants utilize that soil, it resembles less and less whatever its parent material was, okay? Other things that can influence your soil, your climate. How much does it rain? How quickly does your water evaporate? Okay. This is probably the most consistently important factor in making your soil. Because take here, for example, our soil would look very different if we got 50 or 60 days of rain a year, right? Then again, our soil would look very different if we got 1 day of rain a decade. The amount of precipitation we get and the temperatures we generally have dictate what our soil looks like here. Same for my example in the Amazon. Same for everywhere else in the world that has a different soil than us. Interestingly enough, biology also plays an important role in the type of soil that you can see. There are types of bacteria that work to break down organic content. The more of that bacteria you have in your soil, the more broken down the organic content is before it gets incorporated into the soil and things like that. Sometimes it'll actually make it easier for plants to utilize that organic material if the bacteria has broken it down enough, okay? Then you can have, the plants themselves can influence the soil. For example, a pine tree forest. Have you guys ever been inside a pine tree forest? Yeah? How many other plants that weren't pine trees did you see in that forest? Not many, huh? Now imagine you're walking through more of a kind of a temperate forest, okay, where you've got lots of oak trees and sycamores and apple trees and things like that. You can barely push your way through it. The plants there are so dense. Why is there a difference between those two types of forest? Pine trees have evolved a special ability. When their pine needles fall to the ground, they release an organic acid into the soil. That acid makes it nearly impossible for any other plant to survive in that soil. It kills them before they can get too big. Which is why when you're walking through that pine tree forest, you'll usually only see pine trees plus a few other types of plants. A few other plants have actually evolved the ability to survive that acid over the years. But for the most part, other plants cannot survive in that soil, and so pine tree forests typically are only pine trees. Okay, so the plants themselves can actually influence the soil. That's what my parents had to deal with when they moved up to North Idaho. They live about 40 miles from Canada in North Idaho. Okay, full-on pine tree forest up there. My mom wanted to plant some fruit trees, a little orchard on their property. They bought 11 acres. But when she tried, her first couple attempts failed. The trees kept dying. And then she tested the soil and found that it was extremely acidic. Well, she didn't bother to ask me. I could have just told her that, right? Afterwards, I was like, huh, Mom, you did a soil test before you asked your geologist son what I thought about it? I was like, I could have just told you. It saved you some time. But so she had to put some material, some special stuff in the soil to neutralize the acid and then replant her orchard. And now she has some beautiful pear trees and apple trees and blueberries, and it's fantastic what she's got out there. But she never would have been able to do that without neutralizing that acid first. All right. Topography can also influence your soil. Topography is the study of elevation. Okay? Elevation. Bless you. Elevation is relation to sea level. Okay? And we're actually going to have a whole lab on the subject of topography and reading maps and studying elevation. That's lab 5. Okay? That'll be close to the end of the term. For now, though, the elevation of my area in question plays a role because the higher I am in elevation, is it getting warmer or colder? Colder. Oxygen is different, like the atmosphere is different, I mean. Colder generally. Okay, so your soil is going to respond differently to those conditions. But also, what is the angle of my slope? Why would the slope angle make a difference? If I have a very steep slope, what's my soil going to do? Yeah, it's more prone to just fall right off my slope. Bingo, I'm not going to be able to retain water in my soil. So even if my soil stays there, it's not going to have high enough water content for a lot of plants. By the same token, what happens if I have no slope? Oversaturation. That's how you get bogs, marshes, swamps, etc. Okay, there's not enough slope for my water to run away. It builds up and you get oversaturated soil. All right, well, what if my slope isn't facing the sun? I can't grow plants where they can't get sun, right? So these are all factors that influence how successful and what type of soil we have. Now, when you dig down through the soil, oftentimes you will see changes in color. Any of you guys ever worked construction? Ever dug up your yard or anything like that? Yeah? Do you ever notice a change in the color of the soil as you go deeper? That's what these are. These are called soil horizons. Your top layer is called your O horizon. That's where your decaying organic material is. Your dead leaves and sticks and trees and squirrels are there in the O layer, okay? Then you get your A horizon, which is typically called topsoil. It's the rich, dark water and air and organic matter and mineral content, perfect combination. Plants love it, okay? That's where plants typically live. You can buy topsoil at your garden store. That's what you'll usually put in your garden plots when you grow stuff. I'm actually really excited because I finally decided that my kids are old enough, I've wanted to do it for years, that my kids are old enough that I think we can have a little garden. So I'm going to get one little garden box, probably in March or so when things have warmed up enough for it, and I'm not afraid of a freak freeze coming out of nowhere.
What time did you say was the year?
Probably March.
I'm pretty sure it was like snowing or freezing in April last year.
Yeah, but that was atypical. We'll see what conditions look like. If you think, all right, there are plenty of places way, way, way less predictable. But yeah, probably around then. We'll see what conditions are like. If it's not right, then I just won't do it. But I wanna give my kids some experience growing plants. I got that as a kid. No matter where we moved, we always had a little garden somewhere. I was always in charge of potatoes and bell peppers and onions. I called it the breakfast plot. Oh, it was so good.
My history teacher from last semester said he grew pumpkins.
Nice. Yeah, we grew pumpkins once. Pumpkins are fun, and you can do a lot of interesting things with them, but you also have to be really careful with them, because if you don't watch them and if you don't move them so that they have the right exposure and they're not getting wet, they can rot really easily. You got to make sure that they're not sitting in water or anything like that. But yeah, it can be really fun. But anyway, so this year I'm gonna do a garden with my kids for the first time, and I'm really excited because I love gardening. And I don't know, my youngest is he's kind of a demon child. So even today, the only issue that I might have is that I'm afraid I'll come home from work one day and he'll have helpfully gone out and ripped everything up. An early harvest, so to speak. Right? So we'll see. But I'm pretty sure that I can finally do it this year. I think they're responsible enough. I think he understands consequences enough to know he shouldn't do that. All right, so then we have our E horizon, the zone of leaching. This is where all of the stuff that kind of gets, the good stuff gets pulled out, gets sucked out by plants. This is where the rest of it goes. The zone of leaching. That means that anything really good, all the yummy stuff, has kind of been leached out. Okay? Underneath of that is the B horizon, called the zone of accumulation. This is where all our clays, under the pressure of the stuff above them, kind of get squished flat. So clay minerals actually are flat. Okay? They are naturally flat shaped. So up here, when our clays are in that topsoil, they are kind of in these random orientations, like so. Okay? Which allows water to freely flow through them. But any of the clays that get pushed down here to the B horizon, because of the weight and the pressure of whatever's above them, they get reoriented flat on top of each other. Now that makes what is called a hydrophobic layer. Water does not easily sink into it. It tends to flow over it. Okay? So, have you ever heard of, and underneath that is the C horizon, which is just the breaking down parent material. Okay? Have you ever heard of the Dust Bowl? Talk more about the Dust Bowl in a minute, but for now I'll just say the Dust Bowl in this part of the country was catastrophic because it removed pretty much all our topsoil, leaving behind, in most places, just E and B horizon soil. Have you ever wondered why it floods so much whenever it rains here? No? You've never wondered that? Chiangi. Okay. Why does it flood so much? Because we have so much compacted clay near the surface, the water cannot flow get soaked into the ground as effectively, and so it flows on top of it, making the flash floods that we have here all the time. Okay. Now there are 12 different series and orders and 19,000 series, different types of soil. You do not need to know any of them. I'm just mentioning this because it's kind of an inefficient system. We have so many different types of soil, but this is only the United States system. Every other nation has kind of a different way of classifying soils, which makes it really difficult when you're trying to collaborate across borders to do something with soil studies. Okay, but there's a lot of them. I give you the different orders here in case you're interested in looking at those. So let's see. Now that we've talked about what soil is, what it's made out of, I want to talk a little bit about why it's important, how we affect it. When I say rainforest, what's the first thing you guys think about? Amazon. Okay. Emma, I say rainforest, do you think? Let's try that again. I say rainforest, you think, first word that comes to mind. Pop, rainforest, go. Cafe, rainforest cafe. Okay, cool. Actually, rainforest cafes are really fun. Okay, lots of animals, sure. Naomi, I say rainforest, do you think? What was it? Forest? Yeah, it's a forest. Okay, now in the context of humanity. Ulani, I say rainforest and you think? As far as humans and rainforest are concerned. In the context of rainforest and humanity together, like our connection, our influence on rainforests. Huh? Yes. Deforestation. Right? Are you aware what deforestation is? Yes? Do you know how much it occurs? A lot. A lot. Thousands of acres a day. Okay? When you deforest, when you chop down the trees in a rainforest, it's actually a lot more damaging than people tend to think. You're not just cutting down trees, you're affecting the whole ecosystem at a deep level. In a rainforest, you have a very thick O horizon, a thin A horizon, and then a massively thick E and B. Why? Well, in a rainforest, your plants do not grow thick roots. They do not grow deep roots. In a rainforest, plants grow quick and die fast. So whereas out here, maybe you have a tree that lives for 40, 50 years, over there, your trees typically only live for maybe 10, okay, depending on the species. Why? Because they compete, the vegetation is so thick, they are constantly competing for resources with each other. So the roots don't go deep, and they really only cycle the nutrients of the previous plants that lived and died there. So a plant lives, it dies, it falls to the forest floor, it gets incorporated into the thick O horizon, and then the other plants utilize those nutrients to grow. They don't really go down to the deeper layers of soil, and so the deeper layers of soil are completely unutilized. So when you strip off the trees and the layer of soil right under them, you expose all of this unconsolidated, thick layer of clay. What's going to happen the next time it rains? No, it's actually going to carry that clay away. This is the Amazon River Delta where it flows out into the ocean. What do you see? Look how muddy that water is. It is that muddy because of the amount of deforestation we have done, exposing so much clay soil to just getting washed out to sea. Doesn't look good, does it? How great of an ecosystem do you think it is for the fish and other animals that live in that river or out in that delta?
They probably adapted to it by now.
Many have died off.
I don't think they'd be used to like all the minerals in the clay.
Yeah, how much do you enjoy, if there was one big dust sandstorm in Odessa constantly, how much would you enjoy breathing that all the time? Wouldn't it be great? It wouldn't be great. Would we survive? Yeah, sure. Would life be good? No, not so much. Visibility, shot. Breathing quality, terrible. Imagine the, huh? Accidents all the time. Yeah, breathing problems, dirt in your eyes, right? It wouldn't be great for us. It's not that great for them. So biologically, not great. Also, that's a lot of soil that can never be used for anything. It's washed out to sea. We'll talk more about this concept of deforestation in a minute. By the way, this is the city of Angkor Wat in Cambodia, I want to say. It's like an 800-year-old city. It's made out of bricks that they used making rainforest clay, which is why it's that same color there. Very, very compact, dense, hard bricks. Excellent building material. Okay. So when soil is transported away, this is called soil erosion. Remember, erosion is the transport of soil. This can happen via wind or water. Without soil, you cannot grow things. That means naturally grow things, but also crops. You cannot grow things with crops, okay, without any soil. So this brings us back to this point I was talking about earlier, the Dust Bowl. The Dust Bowl happened in the 1930s. Can anyone tell me what happened with the Dust Bowl? Anyone remember? You don't remember learning about it at all? Does it sound familiar, though?
I mean, yeah, I've heard the term, but I really don't think we ever went over it unless I slept through it.
I remember the Dust Bowl. All right, ancient Emma, tell us about the Dust Bowl.
Big Dust Bowl, storm, whoosh. Everyone had to like put rags in their like house and stuff to keep the dust from coming in. Farmers were kind of SOL at the time because of the sand and couldn't grow stuff. And
Yep. And this is all true. The Dust Bowl happened as a result of a few things. Over-farming for about 100 years, okay? So when you use the same soil over and over and over and over and over, not only do you reduce the water in that soil, but you also reduce the organic material in that soil, binding it together. And so it gets drier as time goes on. But then you combine that with an extended drought. We've had a few micro droughts here where we go a year or two with very little rain. Well, imagine 5 years without any. Okay, you combine those two factors together and then all of a sudden you get a windstorm and yeah, feet of dirt, of soil were removed. As a matter of fact, this guy, his arm is at the level where the ground was before the Dust Bowl, and now he's standing at where it is now. Okay? That much dirt over hundreds of millions of acres in this part of the country. Odessa was affected by this. Okay, this part of the country was blown away, washed this way and that way, and pushed here and there and everywhere. And yeah, it covered houses, it covered entire towns, had to be abandoned. It covered, people driving down the highway got buried. It was bad. Okay, people died, but more than anything, it sliced the head off this part of the country's agriculture. Okay, for years people couldn't grow anything because their soil was gone, and even if you had soil enough to grow with, you couldn't count on before the end of the season your whole field not getting covered in these massive dust storms that were blowing through the country. Okay, so this lasted for a while, and then finally that drought ended and they got rainfall and it kind of settled things down. And now here we are, and people are finally able to grow things here again. Okay, but it was a lesson, a very hard lesson to learn about how to take care of your soil better. So since then, we've been paying better attention to it. What exactly is it that soil can do that is so damaging? Well, about 24 billion tons of soil is washed into the ocean or freshwater sources every year. 24 billion tons. That's soil that we can't use anymore. It's gone. It's in the water now. And sometimes it brings things with it. What do farmers put on their crops to make them grow faster, or put in their soil, I should say, to make them grow faster? Well, but that doesn't help it grow faster. You're right. We do pesticides. We'll come back to that. What do we call plant food? There's a word for it. It starts with fertilizer, okay? Yes, it's fertilizer. Exactly. But yes, you're right, it's plant food. Plants love nitrates. Plants need nitrates. Plants grow faster with nitrates. Yes, so the nitrates are in the fertilizer, which gets worked into the soil. The soil gets washed into the water. The water is now high in nitrates. You know what else loves nitrates? Water plants, algae. So you get nitrates in your water. You start growing algae out the wazoo. Algae sucks in oxygen. Your water is now deprived of oxygen, which kills off everything else in your water. We call this an algae bloom. These are really, really bad. Happens when fertilizer gets washed into the water supply. Okay, well now Lexi mentioned pesticides. What do pesticides do? Yeah, they kill bugs and other pests that try to eat your plants. You know what else they kill? Everything else. So you get pesticides washed in your water supply, it's going to kill stuff, including people, by the way. People have gotten really sick and even died because of pesticides that they drank that got into their water supply. Okay? So aside from that, there's the physical fact of the soil itself. If I'm washing millions of tons of sediment down a big river and into, say, a reservoir or a lake, it's filling in the bottom of that water body with sediment. What's the water above it going to do? If I'm filling in the bottom layer after layer with sediment, what's the water above it going to do?
Push it down.
It's going to rise. Yeah, so as the bottom of my lake rises, the top of my lake must rise as well. And it can only rise so far before it spills out and starts flooding the nearby areas. So the less I take care of my sediment getting washed into that lake, the more likely it is I'm risking that lake or reservoir flooding outward and endangering the communities and crops and everywhere else that's around it. So there are a lot of effects that can come from not being careful with our soils. So how can we be careful with it? How can we mitigate these effects? Well, there are a few things that we've learned. You can put windbreaks up. These are trees, often pecan or other trees that you can make some sort of profit off of, or bushes that you put in front of your fields to cut the energy of the wind, absorb the energy of the wind, so that before the wind reaches your fields, it doesn't carry your soil away, okay? Those are called windbreaks. You can have terraces. So if you happen to have fields on hills on your property, you basically cut steps into it. And then every time it rains, your soil gets washed down step to step to step instead of all the way down to the bottom of the hill. So you can use that soil over and over and over on each successive step, okay? And then there's crop rotation. Crop rotation, pretty easy to comprehend here. If I have a field, I might need to throw this pen away. Brown is not showing up very well. Okay, if I have a field, instead of using that field to grow the same thing over and over and over, wheat, that's what we did that caused the Dust Bowl in part, okay? You plant crops in there that complement each other. So for example, corn and beans, great example. Corn, excuse me, pulls nitrogen out of the soil as part of its growth process. Beans pull nitrogen out of the atmosphere and put them in the soil as part of its growth process. So if I have corn here, and beans here during my spring crop season, and then during fall I switch it so that there's beans here, corn here, I can use the same soil to keep growing profitable crops without exhausting my soil. I am continually replenishing the same thing that I am taking out of the soil every season. Okay, this is called crop rotation. We can thank our founding fathers for this. I've been to George Washington, Thomas Jefferson's estates where they experimented with this, and they, among other people, figured out the best crops to use and how to extend the lifetime of soil and things like that. People forget that they were farmers too. Okay. Go back to our conversation about rainforests. Why do we chop down rainforests? Paper. So turn the trees into paper?
Clear out land to make houses.
Clear out land to make houses. Partly true. Unfortunately, not all of those trees are turned into paper or even used for their wood. An unfortunate amount of that wood actually gets burned. This is a crime. But for houses, some places are cleared, but the population of Brazil is not growing so fast that we're getting that many communities in the Amazon. What else?
To build factories.
Industrial space, again, some of that, but the industrialization of the Amazon is not going at that rate either. Some of that, but definitely not the main reason. Any ideas over here? Why are we chopping down rainforests?
Just materials from the trees, like nutrients and stuff we get from the trees and use for somewhere else.
We use some of the wood, but again, an unfortunate amount of it gets burned.
Is it like to make it easier to access the like whatever's under the ground,
What's under the ground?
possibly oil and stuff?
There's some oil, but that's not the principal reason. You are right, it is for a mineral resource. This. We call this bauxite. Bauxite is the richest source of aluminum, ore, I should say, on our planet. Now, why would aluminum be important? Why would we care about aluminum so much? What do we use aluminum for?
The conductor. What's it?
I mean, yes, it has some
To cover our leftovers.
aluminum foil. Yes. Oh man, I have my opinions on aluminum foil. The aerospace industry uses a lot of aluminum. Your glasses have aluminum in them. Your laptop has aluminum. These muffin trays in front of you are entirely aluminum. Almost every piece of technology we've got that requires metal uses aluminum. It is extremely durable and also the lightest metal we know. Okay, the lightest, but also very strong. So aluminum is extremely valuable. And the richest source of it comes from under rainforests where we can find bauxite. Why? You remember those A and B, or those E and B horizons that never get used? It's literally just clay. And clay is rich in aluminum. So as time goes on, those layers of clay get compressed deeper and deeper, harder and harder and harder, and eventually make bauxite. You see those little nodules in there, the red and brown nodules? That's almost pure aluminum from the compression of all those clays. Now, is it true that there have been rainforests on our planet for many, 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 many years, hundreds of millions of years? Yes. Is it true that therefore there must be deposits of bauxite around our planet that are not currently under living rainforests? Yes, and we have found some of those, and we exploit those, we mine those. But is it also true that you can spend millions and millions of dollars to try and find where an old rainforest used to be? Or is it cheaper to just go where the rainforests are now? Yeah. It's cheaper to go where the rainforests are now. So why do we chop down the rainforests? We do use the trees for things, mostly. We do use the space for things, sometimes. But the number one reason? We need aluminum. And
So because we're greedy and lazy.
for the most part. But I mean, that's true for so many things.
Exactly.
Right? Aluminum foil, what a terrible waste of aluminum. You use it once and you throw it away. We chop down the rainforest for that. I mean, I think that there are better uses for aluminum. If we're going to use it for something useful. If you took all the aluminum foil in the world, you could probably make a fleet of spaceships with that stuff. Actually make it worth our time, right? But no. This little guy. I'm going to pass that around. Any questions about soil or weathering? Camera, stay with me now.
Hey, you actually listened first.
Yeah, he did. I've unplugged him and plugged him in a few times. And now he actually bothers to pay attention to me. All right. Well, if there are no questions, then I'm going to end the recording here. And we can move to lab time.